Hello and welcome to lecture 6 of the statistical modelling course, which is on the linear model under assumption violations. So in the previous two lectures, lectures 4 and 5, we've developed the classical linear regression model and the theory of least squares estimation and inference, and we've shown that least squares is optimal in some sense. But that optimality was only delivered under a set of assumptions, and in this lecture we're going to ask what happens when the assumptions underpinning the theory don't hold and what we can do about it. So I want you to think of this lecture really as describing a set of practical issues and problems that mean that the models we're estimating are deviating from the ideal conditions that we've conceptualized the least squares model within, deviating from those ideal conditions of Gauss-Markov. And the question is, how do we detect when such problems exist, and how do we deal with them? So let's start with the structure of the lecture. We begin as usual with the learning outcomes, and then I'm going to do a brief review of linear model assumptions, because those are the context and the organizing theme of this entire lecture. I've then split the lecture into two parts. In part one, we're going to look at issues, practical issues and problems to do with model specification and how we can address them. So in 6.3, we'll look at data transformations and model specification, including interaction terms and dummy variables. In L 6.4, we're going to consider the problem of outliers, leverage and influence, or what we call extreme values. What do we do about them if we have them in our data? And in L 6.5, we'll look at the problem of multicollinearity, which arises when our explanatory variables are very heavily correlated with one another. In part 2, we're going to focus specifically on Gauss-Markov violations, and particularly we're going to look at the violation of Gauss-Markov assumption 2. That is the assumption that the error terms are spherical. So in L 6.6, we'll introduce the idea of non-spherical errors. We'll talk about what it means, and we'll look at two very commonly encountered problems in practice, known as heteroscedasticity and autocorrelation. Then in L 6.7 and 6.8, we will consider two solutions to this problem of non-spherical errors. The first is called generalized least squares estimator. It's a generalization of least squares that can handle non-spherical errors. And in 6.8, we will very briefly cover the principle of robust inference, which leaves the least squares estimator unchanged, but makes some corrections to the way that we calculate standard errors so that robust inference can be obtained even when the errors are not strictly spherical. Okay, and so we have some learning outcomes. I will let you go through these in your own time to find out what you should know by the end of this lecture.